So this is a kind of summary of unsupervised learning methods that we have touched upon so far. So we talked of feature space and how we could reduce dimensionality using principal component analysis, where you find directions along which the points are most spread and do that successively. And we also saw kernel PCA. You can also do unsupervised learning along the instance space, and we kind of give an overview of clustering. You can do clustering which is bottom up, where you take instances, pairs of instances, group them together, and again do this successively, not only on pairs of instances but also on groups of instances. So this is bottom up. Top down is largely based on identifying groups. I'll give them different colors just to denote that they correspond to different means. Each cluster can have a different mean, or in general a representative. Okay, these are cluster representatives. Now you might start with arbitrary cluster representatives, and then as the algorithm converges, the cluster representatives become more meaningful. We also discussed some other considerations in clustering, whether we should look at similarity between instances or distance between instances, and then eventually whether we want to do hard or soft clustering, which means whether we want membership of points to clusters to be binary or have a degree associated. Okay, so this is the broad space. So K means clustering was a specific example of a top down clustering approach, and you can try out K means in this applet. We will also see how you can kernelize K means. So what is the K means algorithm? I will keep referring to this simple GIF file which I will share. So here is a GIF file which is showing how it evolves. Starts here. Now the points are not colored, but even these are the cluster centroids, the blue and the green, and the points are assigned membership to the cluster centroids. Again we start. Okay, so I don't know how to slow this down, but as you can see, in every alternate iteration the cluster centroid is updated, and in every other alternate iteration the membership of the points to the cluster centroids is updated. Okay, so the broad idea behind K means is as follows: K cluster centers mu else, you update them, initialize them. The first iteration is just initialization, then it's update, and second is membership of points to cluster centers. That is updated. So you basically loop 1 and 2 till there is convergence. Until no more change is possible. either to cluster centers or to cluster memberships. Instead of saying no more change, you may also say no more significant change. For all practical purposes, no more change. I mean, you can guarantee clustering, convergence of the clustering in an absolute sense. Okay, so what are these two steps? They're fairly simple. So mu L and P, this mu is superscript, I think, PIL, that's the notation. Okay, so mu I is the center of the ith cluster, Pij is the membership of the jth point to the ith cluster of point j to cluster center I. So these are the two equations we are concerned with. Okay. Now you initialize every cluster mean to a different random value, as you saw on this GIF file. You ensure that the blue and the green and the red, the three centroids, are initially in different locations, and then you can compute the cluster membership that minimizes the sum of squared distances of points to existing centroids. Okay, so I mean, it turns out that these updates are very simple. On the slide I will tell you what the semantics is, and on the board I will write down what the exact step is. Okay. So both mu I and Pij are updated in some sense in a way that the following is minimized. Okay, so what you are interested in is minimizing the sum of squared distances from all the points xj to the cluster centers mu i's. I have used j in the superscript, so I will just, in the slides I use j in the superscript. This is what is the goal. Some feature space phi. So the point is represented in some feature space. Now it need not be xj itself, it could be some polynomial, could involve some polynomial terms like we did for linear regression, right? So we are writing phi in the general case. Okay. Now when you find the cluster centers mu i's, one thing you want to do is fix the memberships. Okay, that's again, let's go back to this GIF file. What I am doing, I mean, observe very carefully. In alternate steps, when I am computing the cluster centers, I reposition the cluster centers, the memberships of the points to the clusters, right? The coloring of the points, that remains fixed when the cluster centers are moved. And once the cluster centers are moved, when I am recoloring the points, I fix the cluster centers. Okay. So the cluster center mu I update, the membership Pij fixed. And when I update the membership of point to cluster centers, what do? I fix the cluster centers. So I am not updating both of them simultaneously. Though my goal is to minimize mu I and Pij with respect to this grand objective, I don't solve for both of them at the same time. I solve for one, I fix the solution for that one, solve for the other. So what's exactly happening is as follows. So step number 1 basically says I am going to use my Pij from the previous iteration. So find my mu I, that minimizes the sum over I, the sum over j of Pij from the previous iteration. I am calling it Pij t, so that I can find my mu I t plus 1 of phi xj minus mu I now square. All the mu's. Yes. So when I say mu I mean the mu i's. Okay, everywhere that's implicit. Mu i's, Pij's. His question was, is it a single mu I or all the mu i's? So it's over all the mu i's, it's over all the Bij's. So this is what step 1 is doing. Now tell me what step 2 is doing. So step 2 is redistributing the points to the cluster. So when you say redistributing the points to the cluster, you mean to the cluster representative. Okay. Cluster centers, cluster or cluster representative. But when you are redistributing to the cluster representatives, what do you keep fixed? When you redistribute the points to the cluster representatives, you hold what fixed? The representatives themselves. So you don't move both, right? You want to optimize, you want to optimally fix the goalpost in your football field, right? But you will get very irritated if the goalpost is being moved as you are kicking your football. And you say, fix rakho bhai, main goal maar raha hu. I mean, let me score my goal and then you can optimize your goalpost, right? So you do one thing at a time. So that's the second part. Min over Pij's summation over I, summation over j of Pij. But what you are going to now fix from the previous iteration is mu, not previous iteration but from the previous step, is mu I t plus 1. So comment here is, it is just not minimizing Pij's but minimizing Pij's such that they are, each point is assigned exactly to one cluster. Okay, so to incorporate that constraint, we can say Pij in 0 1 such that each j goes to exactly 1 mu I. Each xj, each point xj goes to exactly 1 mu I. Again you see that there are no shades on the points. The points are either blue or red or green, right? Their membership may change, the points are not changing, the points are fixed, but their color changes from green to blue to red, might change, which means they have exactly one membership with one cluster, I mean, this is exactly like, you cannot be present in 2 classes, you can't register for 2 courses in the same slot, they are exclusive, right. So this is a partition, it is exclusive. Okay, so that is what hard clustering is about. Hard clustering is that you are dealing with partitions and exclusive membership. Okay. So now let us write down the update equations. I want you to help me identify what these update equations are. So update cluster assignment, update cluster centers, update cluster assignment, update cluster center. You see the title at the top, that is exactly what is happening here. Update cluster assignment, cluster center. Only one is happening at a time. And if you want in words what we are doing in the steps 1 and 2, yeah, exactly this. Okay, so roughly speaking, this is step A, this is step A, whereas 2 is step B. Yeah, so please help me identify what these 2 steps should be. Mu I t plus 1, what will be the mu I t plus 1? That will minimize the sum of squared distances based on exclusive membership. How many of you have figured out the first step? So have you got an expression? Did any of you get the expression? So you don't really need mathematical optimization here, it's basically intuition. Moment you decide that you are going to fix one and optimize on the other, the solution should be fairly obvious. Okay, so here, I mean, we are calling it centers, means, so that should also tell you what we expect that to be, right. So it should be mu I t plus 1 should be the mean phi for all the points that lie in that cluster, and that you can compute by summing over all the j of Pij phi xj divided by the number of points in that cluster, which is summation over j Pij. Is that clear to everyone? Now if you want, you can be more explicit, you can say t, Pij, put a t here, the previous iteration. And this one, the second update, will be what? So you can say this is 1 if ith, so jth point is assigned to ith cluster if point j is closest, right. So is 1 if so mu I t plus 1 if it turns out to be that center which is closest to Pij, closest to phi xj. Okay, so let us quickly verify this. Okay, so this is what is happening. So P for each j, I star is argmin over L of phi xj minus mu t, then P R I star j is 1 for that cluster, and Lj, PLj is 0 for all other clusters L not equal to I star. Okay, so this is the update for step B. That's exactly what I have written there. Okay, that's and text I have written. This can be shown to be minimizing sum of squared distances with the mu LTs or mu ITs fixed. So we have done this t plus 1 and this t. I mean, the indices are not very important. You can get this. You can think that t is getting updated here or t is getting updated here. Well, on the board I have assumed that t equals t plus 1 is happening on this arrow, right? In the slide I assume that t equals t plus 1 is happening in this backward arrow, but t is just an index, it doesn't really matter. Okay, the board assumes this is the update. So basically you want to use the previous mu, that's it. And here mu t plus 1 gets then basically updated, exactly what you said, the mean of all points that belong to that cluster. Okay. No, it's just that indices. So what will you pick in the final? Finally, what will you pick is a question. You should compute the membership again. Yeah. So if any parameter mu has changed, increment by t by 1 and go back to step 2. So we have done that. Okay, so the claim is that this k-means algorithm will converge in a finite number of iterations. Okay, if you go between 1 and 2, you will not have to do this indefinitely. Finite may be large number, but finite number of iterations. And you see that in the GIF also, that for no configuration will it happen that the number of assignments will, the assignments will keep going ad infinitum. And you can prove it. This is a problem in tutorial 6, but this is the sketch. The sketch is basically on the board itself. We want to minimize this objective and we split it into two parts, where in each part we kind of fixed one component, one parameter. Now when I do this, I mean this is the hint given here, when I minimize in step A or step B, is this overall objective reducing? Let us say this is exactly the solution A, right? Now if the configurations have changed, right, keep doing this till there is no change in configurations. So if the configurations have changed, it means that the objective has reduced. Is that correct? The same objective here, here and here, the objective has reduced. So if the objective is reduced in A, if the objective is reduced in B, now how many configurations are possible for Pij? This Pij, how many values are possible? So it's only a finite number of combinations of Pijs that are possible. And what are those finite number of combinations? So if, for example, if I have just 3 points, let us take a simple example, point x1, x2, mu1, mu2, right? So what are the possible configurations? It's possible that x1 goes to x1 goes to mu2, x2 goes to mu1, or it's possible that, I will mark all of them using colors. It's possible that both of them go to a single guy. It's possible that, yeah, these are the two possibilities. Or finally, it's possible that x1 goes to mu1 and x2 goes to mu2. Right? So there are exactly blue, green, red and black. Those are the only 4 possible configurations. So this basically means how many? If there are L clusters and N points, here are 2 clusters and 2 points. How many values of number of So, it is a partition. Is it an L to the power n, somebody said, is it an upper bound or the exact value? So, take a cluster, for a cluster any of the n points can belong to it, for the next cluster any of the n points can belong. So, certainly the number of configurations is less than equal to L to the power n, less than equal to. Now, we have discounted the fact that a single point cannot belong to multiple clusters, which is still okay. So, this is an upper bound. Can you get the exact count? L choose n. Well, n could be much larger. L plus n choose? L plus n choose L? Pardon? So, L raised to n, does it allow you to have a single point assigned to multiple clusters? It doesn't allow? It does allow, right? So, it turns out this is exactly correct. It is L raised to n. So, you take a point, you can assign to any of the L clusters, take the next point, assign to any of the L clusters, right. So, it is L raised to n, and this in this case it turns out to be 4. Okay, so there are finite number of combinations and this objective decreases at every iteration. Okay, let us write down the so L raised to n to be specific, and the k-means algorithm reduces the objective, this particular objective, at every iteration, reduces by non-zero amount. Okay, by an amount greater than 0. So, if this happens, there are only finite number of combinations and the reduction is guaranteed, then obviously the algorithm must converge. The problem would have been if you kept iterating even if there was no reduction in the objective, but we know the reason we are choosing a new configuration is because the new configuration, there is a different configuration than the previous one, which means the objective reduced. So, this is a very simple idea. Okay, so this is the basic idea behind convergence. Now we will try and kernelize k-means. So, k-means kernelized. So, what we will do in kernelizing k-means is we will replace mu l with a phi l, phi of mu l. We will assume that mu l is a point and phi is its feature representation, just so that we can talk about dot products. Okay, and our key observation is as follows. So, let us write down phi of xj minus phi of mu l, the whole square. Expand this, and this is 2 norm squared. Now, please help me write this down purely in terms of dot products. It is very straightforward. So, this step is very straightforward. Yes, everyone. So all of you observe this. You have 5 xj square, 5 mu l square and a 2 times 5 xj transpose mu 5 mu l. Everyone observes these 3 components. What is the first component? So 5 xj is norm square is 5 xj transpose 5 xj, which is, so you could think in terms of, let's just write this down. This is 5 xj transpose 5 xj, this is 5 mu l transpose 5 mu l, and the third component is 5 xj transpose 5 mu l, right? Okay, so now what should this tempt you to do? The first component could be thought of as kxj comma xj. The second as k mu l comma mu l. The third as kxj comma mu l. Is there a question that bothers some of you? What is this mu l? Whose phi I am able to compute? Okay, so all we are saying is, well, this mu l is the point in the x space and phi mu l is the point in the phi space. I am not going to compute phi ever if I use kernels, right? The whole idea of kernels is to bypass phi. But for the sake of convenience, I am going to still say that there is the cluster centers exist, but the cluster centers are in the x space. The phi's are never computed. I will directly compute the k. Right. So question is, if there is a mean, you take the mean in the higher dimensional space, it may not have a corresponding point in the lower dimensional space. That's not exactly what we are trying to say. We don't, what we are trying to say is, we don't need to compute the phi in the higher dimensional space. So our algorithm will change. So the steps 1 and 2, that's why I erased all of it, right? Steps will look different. Okay, steps will not be exactly the same. I mean, the idea is the same. But first let's understand this. Is this clear to everyone? So, and this was the backbone of our k-means algorithm, which is computing distance between points. I mean, that's what we will do here also. Minus 5 mu l square. This remains the same. But how you now, what are the 2 steps you'll need to see. Okay. So if you want, you can expand this. Now you have the squared k xj comma xj plus k mu l comma mu l minus 2 k xj comma mu l. This is what your new objective will look like, right? Now how will the steps look like? Please help me figure out what the steps should look like. What will be Pij update, and here again we will assume that we will alternate between computing the mean, but what is the mean going to correspond to? I will compute the Pij's. So what was the mean earlier? Mean was an average of points in the phi space, right? Now the mean will be what? So you're basically computing the mean in the similarity space using the similarity. Okay, so let's just note the point of divergence from the previous case. So take note of these 2 points here. Phi does not have to be computed for each instance or even for the cluster, means because computations only depend on kernel evaluations, right? And then computing k x mu k comma mu l and k x comma mu l, remember that phi mu l is the average of the phis of the data points assigned to cluster L, but without having to compute them explicitly, because obviously phi could be infinite dimensional and I don't want to compute phis, then the whole purpose of kernels is defeated. What would you do then? So what is it that we are trying to minimize? Now I say minimize with respect to ij. So I certainly have Pij's to be minimized. Now what is mu L? Should I write minimize with respect to mu L as well? If I write minimize with respect to mu L, then I will do this alternating thing like before. So his point is we should not get mu L explicitly, we cannot, rather we will express them as linear combinations, but my point is linear combination of the phis, but we don't want to compute phis, otherwise the whole purpose is defeated. What would you do then? So let me give you an idea of how kernel k-means looks like, right? So this is what kernel k-means would be. Let's say using RBF kernel, k-means is very naive, just the linear kernel or the normal k-means, right? This is, so normal k-means is the linear kernel guy. Okay, I will not have to write linear and normal separately, linear will mean normal. Now you see this, the points outside, I would have thought they are, so let's say I want to cluster the meteors or say, so the intercelestial objects separate from the planet, right? So there's a earth here and there are some things going around it, some satellites going around, say a planet. How many satellites does Jupiter have? Huh? Just imagine you had Jupiter in the center and it's 60 odd satellites in the periphery, in that circle. So I want to cluster, k-means is very stupid. It says आधा Jupiter आधा उसका satellite एक cluster, the other आधा is another cluster, and all of you are laughing at it, right? Doesn't make sense. But if you use RBF kernel, you will get something like on the right hand side. Now go back to mu. I mean, will mu of the two may just directly coincide, right? Mu of the satellites and mu of the planet may just be in the same place. Doesn't make sense. The two we should get confused completely. So we don't want the phi of mu to be computed ever. But note that we get clear clustering. Now this is good, no? You are not happy with the kernel k-means output? No, this is kernel k-means with RBF. And k-means, you can think of this as k-means, or you can think of also it as a kernel k-means with the linear kernel. In fact, that's a good test is that your update rules for kernel k-means when you use linear kernel should coincide with the steps A and B. So that's a test for you guys. Okay, I'm not going to spend more time. I'll leave this as homework because we'll anyways discuss this during a tutorial and as part of your assignment. Right, and this is roughly what is happening here using the RBF kernel. You're basically creating these small circles of influence using the RBF kernel. That's what kernels do, right? They create these fields, receptive fields around your points. I mean, this is a silly thing, but if you use an RBF kernel on this is a nice point, right? We have a nice clustering problem where linear kernel gives you 3 partitions. Now, because the points are little spread out, RBF kernel tries to fit itself to the noise, right? And this is typical even in classification. We have seen that overfitting is possible with, say, polynomial kernels. That's what we see here also. Clustering can overdo, kernel k-means clustering can overdo the clustering. We see a bit of sensitivity to noise. Yeah. Yeah, I mean, because I talked about Jupiter and its satellites, this sounded like weird. See, ultimately, clustering is subjective. So his question is, maybe the left one was okay in some cases. Yeah, all I'm saying is, I mean, it's little intuitive that given that there is a clear separation between the center and the periphery, that the two are separated. So I'm just appealing to intuition, but you're right. There could be some special case. So that's why clustering beyond a point, you have to understand the domain. We can't talk about it independent of the domain for long. Okay, so now we are moving from sigmoidal perceptrons. We talked about unsupervised learning. We'll move back to more complex models, and specifically the 2 drawbacks of perceptrons that we want to focus on. The first is that perceptron does not find the best separating hyperplane, and all of you are all too familiar with this problem. So given the negative points this way and the positive points here, right, you will find that the separating hyperplane might just land up passing through the positive guy. I mean, you are not probably even giving sufficient breathing space or margin, and you know there are multiple separating hyperplanes possible. So it turns out that you can do large margin classification using support vector classification, and I am going to just touch upon it, not go into too much depth, but I want to specifically highlight what this large margin means. The second thing which will take up more time is perceptron can only address linear separability data. Now we have already talked about kernel methods at length. The problem, however, with kernel methods is that the kernel has to be very carefully designed. If you overdo the kernel design, like we saw in the case of clustering also, right, you might become sensitive to noise, you might overfit. So the sensitivity design of appropriate kernel, else you are overfitting, and sensitivity to noise, etc. So that will take us to the cascade of sigmoidal perceptrons. Again, something we touched upon earlier, where you take F and then G and then H, basically take a cascade of these, make them non-linear using activation functions. Okay, so this is where we will now move, and then we will see that we can do a lot more. In fact, your next lab, you will see that F, G, H, you could design them for handling images. image, even speech, text data using properly designed FGNH. Okay, so now for the time being, we'll just have a quick shot at large margin classification. So that topic can itself take a couple of classes. So support vector machine, and the thing we are going to harp upon is large margin. What is the notion of a margin? Okay, and this is the background that perceptron does not find the best separating hyperplanes. By hyperplane, it finds any separating hyperplane. In case the initial W does not classify all the examples, the separating hyperplane corresponding to the final W star will often pass through an example. And that's exactly what I was trying to show here. In this case, it's very much possible that the best separating hyperplane just manages to classify and passes through this or maybe even more points. And what the margin maximization is about providing sufficient breathing space. Alright, we would like some breathing space around the separating classifier, which we don't have. It's just like studying for exams a day before the exams. So we want to do this margin maximization. And what support vector machines do is they say, okay, I am dealing with the space W and I have a bias B. I am already kind of dealing with some redundancy in parameters. We have seen many times that you could just take B to be 1. But what we do in the case of SVM is we say let the margin be 1, at least 1. Find a W set that the margin is at least 1, because this 1 is relative to W. So you scale W according to that 1. So this is the margin we are talking about, and this is the margin we are talking about. For y equals plus 1, the positive points, you have plus 1 and the length of the margin remains the same, the size of the margin, just the sign changes for negative. I mean, this is how you can formulate it, right? But now let's try and understand what that margin exactly is. See, this plus 1 is margin relative to the kind of equation, the inequality I have written, right? So earlier I used to just say W transpose phi x plus B is greater than equal to 0. Now you have greater than equal to plus 1. Or in the other case, W transpose phi x plus B is less than equal to 0, less than equal to minus 1. But under these inequalities, let's try and understand what the margin means. Right? What's the magnitude of the margin? Okay, so now tell me what the margin would be. The equation of this is W transpose phi x plus B equals minus 1. The equation for this margin hyperplane is W transpose phi x plus B equals plus 1. Now what would be this distance? I said that we are trying to maximize margin. So if I wrote these inequalities, write down my expression for margin. Yes. What would be the procedure you adopt? By the way, what is this? This vector is the direction of W. So what are we looking at? Looking at the length of a unit vector length along this unit vector with direction w between this hyperplane and this hyperplane. How would you compute that length of that vector? If you want, just name these two as plus x plus and x minus. Okay. These are two different points. And let's say I tell you that x plus minus x minus is m times w divided by norm w, m, gamma, whatever. Let this be the expression for the length of the m is the margin. This vector is x plus here, x minus here, x plus minus x minus is along the w. I made this into a unit vector, w divided by norm w, and m is the length along that unit vector. Actually, I should do it along phi x. It's not really x, it's phi x. Phi x plus minus phi x. Okay. I can also do the following. I can take this and this, subtract the second from the first. Can I do that? Get one more system of equations. So this is 1. I'll take, let me call this A, let me call this B. A minus B gives you what? The right hand side will be 2. Plus 1 minus minus 1. Left hand side will be W transpose phi x plus minus phi x minus. B will cancel out. Okay. So this is 1 and this is 2. What happens when I combine them? You get equation 3, but that, what do you get? So substitute this difference m w divided by norm w here, right? So W transpose m w divided by norm w equals to that is m times W transpose W. What is W transpose W? Norm W square divided by norm W equals 2. The remaining last step is very simple. It is m equals 2 by norm W. Now you can think of it as m as this entire thing, or maybe half of it is also m. That depends. People margin whether it's a band between plus 1 and minus 1 or between the separating surface and one of the margins. But proportional to 1 upon norm W, that's more important. The 2 is incidental. Is this clear? Everyone understands how you got 1 upon norm W? Okay. So what we have found is the margin is proportional to 1 upon norm w. Any 2 points on the plane such that x plus minus x or phi x plus minus phi x minus, it's along w. Okay. Now this was assuming that the points are well separated, right? But reality is that they are not necessarily well separated. So forget about getting a margin. The points may even kind of interfere with each other. So what typically is done is you allow a slackness. So slackness says, well, they are on the right side except for some slackness, and the way you write this is, okay, W transpose phi x plus b is greater than or equal to plus 1 minus xi. So let us say xi is the point, minus xi if yi equals plus 1. So this slackness is that the points, the blue points may lie slightly below the separating hyperplane, I mean below the margin, in fact may lie so much below the margin that they may even go to the other side. That is this plus point here, right. This is the slackness xi we are allowing here. I can do the same thing for the other points. W transpose phi x plus b is less than or equal to minus 1, but I will allow a slackness there as well, minus 1 plus xi. Okay, so xi is greater than 0 and it makes the minus 1 less negative and plus 1 less positive. That is the slackness. This is how you deal with the non-separable case. Okay, so this is the idea. So xi is, so that is getting into the details of SVM. So SVM says let us try and minimize the xi. Okay, so two things happen in SVMs. You try and maximize this margin. The first thing you do is maximize the margin, which is proportional to 1 upon norm w, and the second thing you do in SVM is minimize slackness in terms of summation of xi's. All the xi's put together I want to be small. Maximize margin, minimize the xi's such that these constraints are satisfied, right. I mean, I can just make these constraints more compact like before and say if I just multiply yi into both, W transpose phi xi plus b is greater than or equal to 1 minus xi. If you combine these two, okay. So minimize slackness, maximize margin such that yi into W transpose phi xi plus b is greater than or equal to 1 minus xi. These are the three parts to an SVM. So again, first is maximize the margin. We want to maximize this margin. I have already explained this. At this we have found is proportional to 1 upon norm w. X plus and x minus lie on boundaries of the margin. So I am just recapping the three parts. W is perpendicular to separating surface. We project phi x plus and phi x minus on w, normalized by w, since we are only concerned with the direction of w, and that is what gave us this part, maximize 1 upon norm w. Okay. And then this is the derivation. So overall objective, I want to end with this. Overall objective is as follows. You want to maximize 1 upon norm w or 2 upon norm w, the margin, such that the constraints are satisfied, but you also want to be able to do something meaningful with the xi's. Because if you leave the xi is unbounded, what will happen? Xi will happily go to infinity. So, कुछ problem नहीं है, मैं तो बहुत बड़ा बन जाता हूँ. I will classify all the points generously. Margin will become as high as you want. Everyone is happy, but we are not happy because slackness of infinity means that no, to hell with classification. Basically, saying margin बढ़ाओ, classification भूल जाओ. That doesn't make sense. I mean, the whole idea is I want to maximize the margin such that I classify well, right? So this is meaningless. Since we want to maximize margin while classifying accurately. Okay, so therefore what we do is, we say I am going to argmax this and minimize the summation of the xis. I want the xis to be small collectively. Okay, so that's why we want to minimize the xis. So this is basically the objective that SVM solve, and we are going to stop with SVMs here. Not very important to get into the details of SVMs because that requires more optimization, duality theory and all that. But what you do is, instead of maximizing the margin, you minimize the reciprocal of the margin, so that you can also minimize the sum of all errors. So instead of argmax over 1 upon norm w, you do an argmin over norm w square, the reciprocal of 1 upon norm w and its square. So that's very much SVM. I'm not this specific thing. I'm going to no more details. We'll get into. I'll leave you optionals, optional reading material, optional extra reading material I'll leave for you.